What I want to point out is that the compression is typically done at the application layer because it knows the signal model. And the channel coding is typically done at the physical layer because it needs to know the channel model. And it doesn't really exploit signal characteristics. Our approach is that if you use compressive sampling in the first place to do all of your transmissions, then to add robustness, all you need to do is tweak this parameter k and make that into m, where m is a little more than k. Okay? And this is what we call oversampling or compressive oversampling, as the paper suggests, as the paper title suggests. And so let's look at this a little more visually. This is supposed to have some red dots in the middle, but the contrast is really bad here. So if you've got this x signal, you've got phi as your sampling matrix, you've got z as your measurements, and you try to send over this z, right? And you've got missing samples. So you've got some gaps in the middle. Now what these missing samples mean is that essentially your phi matrix, your sensing matrix itself, had some gaps. So what happens if we oversample? So we add more samples here, so more measurements, and we add more rows. Okay. And so we've got the same missing data. So the question is, can we recover this lost data? And how much oversampling is needed? So this paper essentially makes this claim that when m samples are acquired uniformly randomly and sent over a binary erasure channel, that's a memory-less binary erasure channel, the received k samples are still equiprobable. What this implies is that the same sparsity bound holds that I talked about earlier. So in terms of features, I would say that by using this mechanism, you don't need to have an additional channel coding block. You achieve the same redundancy that you had with channel coding with plain oversampling. And a very key difference is that the recovery is resilient to incorrect channel estimates. So when you do channel coding, and if you could not recover from the errors, you drop all of the packets and you retransmit again. In this case, I'll show you that when the recovery is not perfect, you'll still get something out of it. And the decoding is free if compressed sensing was used anyway. So the intuition behind why this works is that channel coding typically spreads information out across measurements. And compression compacts that information in fewer measurements, right? So there are two conflicting or contradictory mechanisms. And what compressed sensing does is it actually spreads the information while doing compacting. So there is some overhead. So we did some evaluation. And so when you look at the performance in terms of recovery, this is the baseline performance with no loss. And when we have 20% loss in our signal, where's the, okay, there we go. So there's a drop in the recovery probability when you have 20% loss on your channel. And when you do this oversampling mechanism, you get back exactly to the baseline performance. Now this is not surprising because this is work on a synthetic binary erasure channel. And so everything, the simulations line up with the theory. This is what it says. And the interesting thing is that when you have 7% or 15% oversampling, you're somewhere in the middle between these two. An interesting case happens in bursty channels where you don't, I'm just going to go quickly through this, you don't get perfect recovery. And that's because you need to apply some sort of interleaving before you do the transmissions. I'm going to skip this, and this is with a real trace from an 802.15.4 channel. And here we show that there is some burstiness, but you can get back to the original baseline with 15% oversampling. So in terms of the computation overhead, we tried to compare 3 different scenarios. One that sensed the data and sent the raw data after doing some Reed-Solomon encoding. one that sends the data, apply compression, and then send it, and this one is using our technique. And we can see that that's about 2.5 times lower in energy compared to the other two. I'm going to conclude here saying that we've shown that oversampling is a valid erasure coding strategy. This is not true if you didn't do compressed sensing. Here we have a bound on the robustness, or a guarantee on the robustness. And for binary erasure channels, we've shown that the oversampling rate can be equal to the loss rate. And we can show that erasure coding can be rateless, and it's also computationally more efficient. I'm going to thank everyone, and we can take questions offline. Okay.
How much usually oversampling you need? Can you find a sort of expression, mathematical expression, or closed form to say? So you have these simulations that